Hello and welcome to Toddcast number 37, starting into elimination reactions. And we're going to cover the E2 and E1 mechanisms in that order. And similar to the SN2 and SN1, you have more of an acidic nature to the SN1 because you can protonate, make a good leaving group, for instance. Same thing's going to be true in an E1. And then you need a good nucleophile, which is a basic compound. So SN2, because of the good nucleophile, was a little more to the basic side. Same thing's going to be true for E2. So similar in the conditions, but a different result. So we'll look into what elimination reactions are and then get into the mechanisms. So we'll start first off with what an elimination reaction is. So as the name implies, something is going to be eliminated. So elimination reactions involve the following. So we talked about substitution reactions where if you have some arrangement here and you have a secondary carbon, then OH can come in and kick out the Br. Well, we also mentioned at the start of that, I should say, uh, that if the base is strong enough, it can actually take a proton. And so it is a very strong base. So we run the risk of what's known as an E2 elimination. And one of the things we want to do just straight away when I get into this, I want you to be able to tell me which comes first, one or two, and which comes first alphabetically, A or B. If you can answer that question, you now know that E1 favors acidic conditions, E2 favors base conditions. So a strong base will lean towards an E2 reaction. So the H that gets eliminated, so you end up eliminating a leaving group, just like substitution, but now you're also going to eliminate an H. And so you're moving those two, you're eliminating those two from the molecule. And so if I just drew, this is not really what it is, but let's say I have this and this, two free radicals, or if I want to think about it where the Br leaves as a minus, then this would be a positive, and H leaves as a plus, this would be a minus. What can happen is these two can form a bond, or this negative can come in there and form a bond. So that isn't what happens. It isn't that they leave as radicals or leave as ions and leave this ionic or well, dipole two ion or zwitterion as it'd be called molecule. This isn't what happens, but conceptually, it's a good spot to start. If we lose an H plus, the negative electrons here can come in here, form a double bond, which pushes out the Br. So it's not exactly ion formation, but it's in that ballpark. So we're going to get a double bond between that H. Okay, one of the questions, just want to foreshadow a little bit here, is I chose an H on carbon number 3 right there. Questions I want to ask is why did I not consider H's here or here? So first off, to form a double bond, you have to be on the adjacent carbon. So the H has to be on the next one. So this one's too far away to form or won't form a three-membered ring. So that's not going to be happening. So it's got to be on an adjacent carbon. So we're going to call this the alpha carbon, and this is going to be called the beta carbon. This is also a beta carbon, which means theoretically, the double bond could have also gone there. Could have gone this H, but food for thought for down the road, reactions like to make a more stable compound. So we have to determine whether it's more stable to have a double bond with two R groups donating to it or just one R group. And so I will leave that as an open-ended question for now, but you have to figure I probably drew the most stable one for this. So there must be something to having more donating groups to make the compound more stable. And then also this double bond, just a reminder, this is known as trans because the two groups are on opposite sides of one another. And so trans is also more stable. So these questions get a little more complicated as we go. So I drew a simple case of just one product, but there would be a small amount of cis and a small amount of the 1 pentene in addition to the 2 pentene, but predominantly you'll get trans 2 pentene. Okay, next case, this time I'm using strong acid, and again, acidic conditions tendency to favor 1, SN1, E1, specifically E1, and then base, strong base, has tendency to favor 2s, SN2, E2, but specifically E2 if it's a very strong base. So strong acid, this OH has lone pairs, it can come over and pick up an H, turning it into OH2 plus, which can leave. When it does, you're going to get elimination. So strong acid is going to cause elimination. So let me go ahead and get rid of what I've drawn there. And remove the H and the OH. And again, I'm going to take something on the adjacent. So if this is alpha, that's beta, beta, and beta. The one that forms a more stable double bond, the more substitute double bond is the one that's going to be the predominant species. Don't have to worry about trans and cis anymore because one of the methyls is cis, one of the methyls is trans. So it's always going to end up being that way. Okay, that's an overview of the reaction. So need to consider the mechanism. Mechanism is going to be huge for this particular topic. So the compound that we looked at had a bromine on an alkyl group. I just want to generically put R1, R2, R3, and R4. They could be H's, methyls, ethyls, some random carbon group, but irrelevant. The thing that matters will be the 2 carbons right here. The one with the H, where the H is getting deprotonated, and the one with the Br, where the Br is leaving. So again, we call this the alpha. One away is the beta. There are beta hydrogens here and here, but I'm ignoring them for the time being. So this is the, just pile on a little information. I know that I have to consider the H on the next carbon, but even more importantly, the way the orbitals line up. And this is our first step into this, but orbital alignment is actually fairly important. Backside attack, the orbitals have to line up the right way. That's why we did it. This time, we also have to have the orbitals line up the right way. And what that means is, if for the base to come in here, if it's lined up the right way where the H is here, then those electrons can literally move in the plane, come down, and push those electrons out of the way. That's how we're going to represent it in a arrow pushing fashion. But also want to consider the orbital scenario. So high temp, I'm going to mention the fact, or want to emphasize the fact that we're breaking 2 sigma bonds to form a new sigma and a new pi. Pi bonds, double bonds are stronger than single, but within it, the sigma bond is always stronger than the pi bond because the pi bond doesn't have electron density between the nucleus. So we're breaking 2 sigma to form a sigma and a pi, which means we're always working uphill. We're always doing an unfavorable reaction. So one of the telltale features of an elimination reaction is you end up raising the temperature a little bit. So higher temperature, if you elevate temperature to above room temperature, you're probably aiming for elimination. If you run at room temperature, that still might be warm enough to get, depending on how good the leaving group is, still get some elimination. So key features, things you have to know. A strong base, because it has to pull an H off a carbon, but it also helps if it's large, because if this is really bulky, then it's going to be too bulky to come in as a nucleophile. It's too crowded, so it's going to settle for taking an H. So the large base, the purpose of it is so that you end up getting just E2 dominating. You don't see a lot of the SN2. Okay, second feature, the H and leaving group must be anti to one another. So if this is up and in the plane, this must be down and in the plane. And that's so that the orbitals are aligned correctly to form the new pi bond. High temperature, again, because you're forming a less stable bond. So it's going to push the reaction forward to form the less favorable pi bond. And the rate, because it's 2, subscript 2 means it depends on the concentration of the base and the concentration of the alkyl bromide in this case, or the electrophile. I'm just going to call it an Rx generically. So far so good. So I want to look at this a little more carefully then. So I want to look at the orbitals, because that whole anti-alignment, we should look at it a little more carefully. And what we'll see is if the H is anti to the leaving group, then this orbital on carbon, this sp3 hybrid, and this orbital, this sp3 hybrid on this carbon, are in the same plane. And they simply have to just rotate over to align the right way. So this is what we have in the beginning. They're aligned correctly, anti to one another. So if the base comes in and attacks this H, so here's this base coming in, it binds the H, so the H hasn't moved. These two carbons actually haven't moved, it's just the electrons have moved over. So this density has gone to here and there, this density has gone there and there, so that's why the orbitals are straight up, and they now share. And the Br has just left. It hasn't even moved. The electrons have moved away from it, but it's now isolated as a Br minus away from the molecule, and it's free to go wherever it wishes. So I want to look at this more carefully. I want to look at these same orbitals. So this time, this is this group here. I haven't put the lone pairs on here, just a little bit lazy, but I care about this pair of electrons. It's going to come in like it does here and bind with the H. When it binds with the H is going to release these electrons. They're going to rotate over. So as mentioned, this will rotate here. This will rotate here. My pen, there we go, a little better. This one's going to rotate up. This one's going to rotate down. And the BR is essentially just going to drop off. So it's going to happen quick. Sorry for the speed of this. But watch as this comes in. Notice the H will stay in the exact same place like it did here. The orbitals, because they're in the plane already, can just rotate over. BR is just going to flop off. So what we had happen, this came in and bonded the H like we had before. These orbitals redistributed their electron density to now form a pi bond in the plane. These two groups rotated up, so they're now in the plane. So this is now an sp2 hybridized carbon. And these two used to be up, they rotated down. The Br, it's free to take off. It's now unbound by that pi bond. So notice that the H, the Br, and the carbons are all in the same spot as they were before, just electron density shifted. So this is going to be a theme you'll see through all of organic chemistry, and for anybody going on like to second semester organic chemistry, you're going to deal with something called electrocyclic reactions, where electrons will move around pi bonds just like this. Literally, p orbitals will rotate around to form different and new bonds, go from sigma to pi. So hopefully this seems reasonable. So we ended up with this molecule, but now specific groups instead of generic R groups. So I had to go with ethyls and methyls. Okay, so key things to remember. Typical bases have to be bulky and strong. So hydroxide, yeah, it'll work, but it's a little on the small side, so it's not optimal. And if I use OH minus, I usually get a mixture of substitution and elimination. So I scale it up. Methoxide, a little bit bigger, but still running the problem. But by the time I get to ethoxide, it starts favoring more and more elimination, because as this gets bulkier and bulkier, it gets harder to come into the carbon. But typically, to encourage it to go predominantly or almost exclusively by elimination, we use extremely bulky bases. One of them is going to be called T-butoxide. Well, sodium T-butoxide and potassium T-butoxide. It really doesn't matter which cation I put on there from an OChem lecture class perspective. It does matter a little bit in terms of what solvent you're using and how soluble the ion will break away in, but we're just going to use them interchangeably in class. And amide, and then specifically another amide where instead of two H's, which is small, we have two very bulky groups. The bulkier the group, the more likely it's going to do elimination. Smaller group, you might get some substitution. This is such a strong base, probably still going to completely deprotonate it. Very, very little substitution. But as dealing with this one, you might actually see some substitution. Okay, so typical bases. You do have to memorize a certain amount of information in OChem. This is just another example of stuff being memorized. Okay, so that was an E2 elimination under basic conditions. Under acidic conditions, We protonate, and I like to do the example with an OH just so that we can emphasize the fact that we're making water as a leaving group. And when water leaves, so when this is going to take off, it's going to take these electrons with it right there, and in doing so, leave behind a carbocation. So high temp, you're going to end up with this carbocation, emphasizing it's tertiary. This H can move over and still be tertiary. So you can rearrange from one tertiary to another. It's just going to be randomization, but you can't go to secondary or primary. You won't get a very large amount of that. So it's going to stay as tertiary. The solvent is going to come in, take this H, and those electrons are going to come in. So it's a two-step reaction where you leave just like what happened in SN1, and then the electrons come in to form the pi bond. The orbitals are doing something very, very similar that we saw in the previous one. So this will be my empty p orbital. This will be my hybrid. In the end, all you've done is these electrons stay in the same spot. These are rotated over to form the pi bond. So orbital alignment is key. Key features of this one. Number one, strong acid. You can use a strong Lewis acid, and it's going to seem weird at first when you see them, but certain Lewis acids could work. We're typically going to use things like H2SO4 and traditional Bronsted-Lowry / Arrhenius acids, but it could be a Lewis acid as well. It could be a very strong metal that cationic metal can behave in similar ways, H+. High temp, again, you're making a pi bond, you have to pump the heat in. Has to have a good leading group, so it won't work with OH, but once you protonate it, it can happen. And something that we're going to elaborate on, and that's called Zaitsev's rule. Zaitsev defines the more stable alkene as one that has the greatest number of R groups on the double bond. So if this is my double bond. If I have H, 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 and H, they don't help much. They don't donate in to make it more stable. But if I have a CH3, then it's better. Or if I have a CH3 and a CH3, that's even better still. 2 beats 1, and so forth. And so what you end up getting is this rule that you want to have the more stable alkene, which is the more substituted. Double bonds want to be internal, not terminal. You have potential for rearrangement when you have a carbocation. That's always something to consider, just like the SN1. And the rate only depends on the Rx. So adding more acid won't speed up the reaction. So, and besides, acid is catalytic in nature anyway. So there really is only one reactant involved, so it can only depend on the one. Okay. So this is what meant by Zaitsev's rule. So unstable when it's just all H's, but when you have one R group, like a methyl I showed another one, gets a little more stable. When you have two R groups, you can have them right next to each other. You can have them across from each other, but cis and trans. Trans beat cis, and cross like on 1, 2, or just on the two different carbons of the double bond beats the two being on the same one. So least stable, next, 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 next. The tri-substituted, and this may not seem like there's much of a difference, but if we have the R group being higher priority than H and R being higher priority than R prime, then the two bulky groups are trans, the two bulky groups are cis. I actually have this one inverted because trans it ends up being more stable than cis. Then finally, tetrasubstituted. So unsubstituted, monosubstituted, disubstituted, trisubstituted, and tetrasubstituted just refers to how many R groups are on the carbon double bond. So Zaitsev's rule, you want to try to get this if possible, if not this one, then this, if not this, then this, and so forth. You want to go for the more substituted double bond. That is your more stable. So your most stable, 4, least stable, none. Okay, so we'll consider this right here. If I use ETO-Na, that's a base, strong base, high temp, so it's going to go by an E2 mechanism. That's what we'll go with. So this one's going to be E2. This same story, E2. but an acid would be E1, and rearrangement only occurs with E1. So it's just recognizing base E2, base E2, acid E1. So strong base leads to elimination by an E2 mechanism. Strong acid leads to elimination by an E1 mechanism. So strong bulky base E2, strong bulky base E2, strong acid E1. So E1, reaction 3 only. So it's one of these things to program in by doing enough questions. This is like a good starting point. And I'm going to elaborate on this one a little more, why I did the exact same reagents here, and it formed one type of double bond here, but a different double bond here. So that's food for thought. But for now, we are done. So I will see you at the next Toddcast, which will just go ahead and continue on the same topic. So thank you. See you next Toddcast. Bye.